Applying L'Hopital's rule in special cases. We could have another indeterminate form, 0 times infinity, if we had the limit as x approaches a of the product and the limit of one of the factors equaled 0 and the other equaled infinity. Because what's 0 times infinity? Which one wins? If they're battling and 0 wins, then we would get 0 times anything is 0. But if infinity wins, infinity times anything is infinity. So if f wins, the answer would be 0. If g wins, the answer would be infinity or negative infinity. Or it could be a compromise, some finite non-zero number. So we would need a way to determine that. And we couldn't directly apply L'Hopital's rule here because L'Hopital's rule only applies for 0 over 0 or infinity over infinity indeterminate forms. Let's look at an example and see what we would do in a case of an indeterminate form such as 0 times infinity. We can see that if we let the limit as x approach 0 from the right hand side, the square root of x factor would be approaching 0, but the ln x factor would be approaching negative infinity. So we'd have 0 times negative infinity. Who wins? Which one dominates? What we do is we do some algebra to doctor it up so that we can use L'Hopital's rule. We can use L'Hopital's rule if we have the indeterminate 0 over 0 or infinity over infinity. So as we're trying to see who's winning this battle, let's express this as the natural log of x divided by 1 over the square root of x. You can see if we inverted and multiplied, if we flip this over and multiplied, it would be equivalent to this. But the reason we would write it like this is because then we have an indeterminate form where we can use L'Hopital's rule. Because as we approach 0 from the right hand side of the natural log of x, we are going towards negative infinity because remember what the natural log graph looks like. So as we head towards 0, we're going towards negative infinity. Looking at the denominator, if we approach 0 from the right hand side of 1 over the square root of x, well, we know that the square root of x as we approach 0 approaches 0, so 1 over that would approach infinity. So now that we have the correct indeterminate form, we can apply L'Hopital's rule. So this equals the limit as x approaches 0 from the right hand side of the derivative of the numerator, which is 1 over x, over the derivative of the denominator. I'm going to express the denominator as x to the negative 1/2 so that I can use the power rule. Power out in front, decrease the power by 1. Now let's go ahead and look at this. The limit as x approaches 0 from the positive or right hand side of 1 over x over negative 1 over 2x to the 3/2. And then simplifying, we will multiply by the reciprocal, negative 2x to the 3/2 over 1. And so we have the limit as x approaches 0 from the positive of, we're going to have negative 2, and this is like 2 over 2, so when we bring it up here and subtract it, it's going to be x to the 1/2. Well, that's equivalent to negative 2 square root of x, and we know the square root of x graph as we approach 0 from the right is 0. Looks like the square root of x won this battle. Let's look at another indeterminate form. If we have the limit as x approaches a of f of x minus g of x, and both of these go to infinity, what is infinity minus infinity? Well, it might be 0, but maybe one infinity is bigger than another. We've got a battle going on. Which one dominates? Again, we could have, if f wins, then we'd have infinity, that one wins, so that would be infinity. If g wins, we would get negative infinity, but there could be a compromise and get some kind of a finite number, or we really could get 0. Infinity minus infinity may be 0. So it just depends. We cannot directly use L'Hopital's rule, so let's see what we could do. Here I have the limit as x approaches pi over 2 from the left-hand side, and I've got secant x minus tangent x. So we know that since the cosine of pi over 2 is 0, we know we have a vertical asymptote there. So we've got an infinity or negative infinity. And looking at tangent similarly, because tangent is sine over cosine, we have cosine being 0 at pi over 2, so we've got a vertical asymptote, and we have an infinity or negative infinity as well. Well, what we're going to do on these kind is we're going to see if we can express them differently. So here we have pi over 2 approaching from the left-hand side. Well, let's go ahead and write this as 1 over cosine x and as sine x over cosine x, so we can see if there's some other way that we can express this. This is the limit as x approaches pi over 2 from the left-hand side of 1 minus sine x over cosine x. Now, if we let x approach pi over 2, if we were using a direct evaluation, the sine of pi over 2 is 1. We'd have 1 minus 1 is 0. Cosine of pi over 2 is 0. So we do have the indeterminate form 0 over 0, so L'Hopital's rule will apply. By L'Hopital's rule, then, we have the limit as x approaches pi over 2 from the left-hand side of the derivative of the numerator is negative cosine x, and the derivative of the denominator is negative sine x. And we now can directly evaluate, because the cosine of pi over 2 is 0, but the sine of pi over 2 is 1. So it looks like our limit is 0. We want to look at one other type of indeterminate form, and that is when we have something raised to a power and we have various combinations here. So the limit as x approaches a of one function raised to another function, and three different things that might happen. The first thing might be if f of x equals 0 in the limit as x approaches a, and if the limit as x of x approaches a of g of x equals 0, we'd have 0 to the 0. Well, what is that? Is 0 to anything 0, or is anything to the 0 power 1? Exactly what would we do? Looking at the second indeterminate of this type, if f of x equaled infinity in the limit, and the limit as x approaches a of g of x was 0, we'd have infinity raised to the 0. Again, how do we determine who wins? And if the limit as x approaches a of f of x is 1 and of g of x is plus or minus infinity, we'd have 1 to the infinity. Is 1 to any power 1, or is anything raised to infinity infinity? Who wins? Now, on all three of these types, we could pull the same trick, and there's actually two different ways to kind of pull off this trick. Could either take the natural log of both sides, so that you could use log properties, and after you have the log of both sides, then you could move this exponent out in front using the third property of logs. Or you could pull a little trick of knowing that e to the ln of some function to some power is equivalent to the function raised to the other function, because e and ln undo each other. But instead of canceling them out, you could use the third property of logs, and you could move this out in front. So these are just two different ways to kind of pull off the same thing, and what we're doing is expressing this in an equivalent form so that we then could see what we could do to find the limit. So let's see an example of this one. What if we had the limit as x approaches 0 from the right-hand side of x to the square root of x? Well, this is a 0 to the 0. Applying that third property of logs, we could move this exponent out in front and multiply it. So we would now have the limit as x approaches 0 from the right-hand side of the natural log of y equals the limit as x approaches 0 from the right-hand side of the square root of x natural log of x. But wait a minute, we actually just computed this one. We knew that we could express this like this so that we could use L'Hopital's rule, and when we did that we found out this equaled 0. So what we now have is the limit as x approaches 0 from the right hand side of the natural log of y equals 0. Well, we need to find this out for not natural log of y but for y, since our original function equaled y. So what we're going to do is we're going to exponentiate both sides, and we know that we can move this function inside of the limit. So we have the limit as x approaches 0 from the right hand side of e to the natural log of y equals e to the 0. Well, the e and the ln undo each other, and so we have the limit as x approaches 0 from the right hand side of y equals 1, because we know, of course, e to the 0 equals 1.